Bismillahirrahmanirrahim. Yokosu. In this video, I will teach you about stoichiometry. So, what do you guys know about stoichiometry? Stoichiometry is the study of the quantitative relationships between reactants and products in a chemical reaction. It uses balanced chemical equations and the law of conservation of mass to calculate the amounts of substances involved. We're going to explore this further in this video. This will be our learning objectives in today's video. Have a read. Apologies for that. This is the clear version. Have a read. Alright, let's start with unified atomic mass unit. Unified atomic mass unit is 1/12 of the mass of the carbon-12 atom. The value of 1U is equivalent to 1.6605 times 10 to the power of negative 27 kilogram. Now, let's move on to Avogadro's constant. Avogadro's constant is the number of atoms in 1 mole of any substance. And the value for Avogadro's constant is 6.022 times 10 to the power of 23 per mole. The relationships between unified atomic mass unit and Avogadro's constant are as below. As simple as that. We can also use the Avogadro's constant to find the number of atoms or the number of moles. So basically, the number of atoms is equals to the number of moles times by the Avogadro's constant. Now let's look at the example. How many sodium atoms are there in 0.05 moles of sodium? Anyone? To find the number of atoms, you just simply multiply 0.05 moles times 6.022 times 10 to the power of 23 per mole. And the answer should be 3.011 times 10 to the power of 22 sodium atoms.
So for today, I will be explaining about balancing chemical equations. First of all, we need to know what is chemical equations. Chemical equation is a symbolic representation of a chemical reactions using element symbols and formulas. Why do we need to balance our chemical equations? So that the number of atoms of each element is the same on both sides of the equation. So now, how do we balance it? Okay, so let's take our first example. For our first example is reaction of hydrogen and oxygen to form water, which is H2O. The left side equation is unbalanced because the left side have only one oxygen atoms, while the result have two oxygen atoms. So, we add 2 at hydrogen to make it into 2H2O. So now, we have 4 hydrogen and 2 oxygen atoms on the right side. Another example is reaction of iron with oxygen to form iron trioxide, or we also can call it ferric oxide or rust. The left side equation here is unbalanced too. It has 1 iron and 2 oxygen atoms, and it doesn't match with the result. To make it balanced, we add 4 into iron and 3 to oxygen. So now we have 4 iron and 6 oxygen atoms, which is balanced.
Mole calculations. For solids, we use the formula N equals to M over Mr, where N is the number of moles, M is the mass in grams, and Mr is the relative molecular mass. For example, if you have 58.5 grams of sodium chloride and its relative molecular mass is also 58.5, then the number of moles equals to 58.5 over 58.5 gives us 1 mole. Then for solutions or liquid, we calculate molarity using the formula M equals to N over V, where M is molarity, N is the number of moles, and V is the volume in cubic decimeter. For example, 0.25 moles of sodium hydroxide in 0.5 cubic decimeter solution gives us molarity 0.25 over 0.5, it gives us 0.5 molar. While for gases, at room temperature and pressure, 1 mole of gas occupies 24 cubic decimeter. So the formula is N equals to V over 24. For instance, if you have 48 cubic decimeter of oxygen gas, number of moles equals to 48 over 24, then it gives us 2 moles.
Moving on to the empirical formula. The empirical formula represents the simplest whole number ratio of atoms of each element in a compound. Note that this does not show the actual number of atoms, but rather the relative amounts present. For example, hydrogen peroxide, H2O2, has the empirical formula HO, and glucose, C6H12O6, has the empirical formula CH2O. This makes empirical formulas very useful in showing the basic composition of compounds in their simplest form. To determine the empirical formula of a compound, we start by finding the moles of each element present. Next, we divide all the mole values by the smallest number of moles to get a ratio. Finally, we round these ratios to the nearest whole numbers to obtain the empirical formula. For example, a compound with 30.4% nitrogen and 69.6% oxygen gives mole values of 2.17 and 4.35. Dividing both by the smallest value, 2.17, we get the ratio 1 to 2, which means the empirical formula is NO2. Now for the molecular formula. The molecular formula shows the exact number of each type of atom in a single molecule of a compound. Unlike the empirical formula, it tells us the actual structure of the molecule. Importantly, the molecular formula is always a whole number multiple of the empirical formula. The relationship is given by molecular formula equals empirical formula multiplied by n, where n is the ratio of the molar mass of the compound to the molar mass of the empirical formula. N here is not the number of moles. To find the molecular formula, we first need to calculate n. Once n is determined, we multiply the empirical formula by this number. For example, for a compound with an empirical formula of NO2, and when the molar mass is 92 grams per mole, we divide 92 by the empirical mass, 46, to get n equals 2. Multiplying the empirical formula by 2, the molecular formula is N2O4.
Hi, I am Alam. I lost my voice from an event last weekend. Stoichiometry tells us how much product we should get in a reaction. That's why we use percent yield, chemistry's way of saying expectation versus reality. The formula is simple: actual yield divided by theoretical yield times 100. Let's say theory promises 10 grams of water, but the lab only delivers 9. That's 9 over 10 times 100, a 90% yield. Still good, but not perfect. In short, theoretical yield is the dream, actual yield is the reality, and percent yield tells us how close we came.
Stoichiometry is used in real life, especially in the pharmaceutical industry. If you look at drug production, mole balance is taken into consideration, where 2 moles of reagent A react with 1 mole of reagent B to create 1 mole of compound C. Stoichiometry guarantees that the mixture contains those exact mole ratios, preventing the production of undesired products, such as excess of either reagents, which is seen as waste, and as an expense to purify, because the excess reagent contaminate compound C. We can use what we learned in yield percentage, which is actual yield per theoretical yield times 100 to calculate the theoretical, and actual yield can help to estimate the exact amount of compound C will be produced from a certain reaction without extra waste.
Alright, that is the end of our video. Hope you guys enjoy, and hopefully it helps you guys to improve your stoichiometry. But before you go, make sure to smash that like button and subscribe for more content. Thank you.